Hi everyone. So today we will discuss sample preparation because that is very important before you carry out any characterization. So we will look at the most important part of sample preparation, which will apply to most of the techniques which you will learn during the course. Specifically when one technique is being covered, you will know more like what you have to do specifically for that particular technique, but this will apply mostly to all techniques. Okay. So that is the idea, because then we will see how to prepare samples for X-ray diffraction, which we discussed in the last lecture. Okay. So critical steps of sample preparation involve sampling, grinding, hydration stoppage and storage, right. We will go over these so that we know how to do it. So sampling is most critical step, right, as you can guess, because it is always a challenge to get a representative sample, right. If you want to get an idea about the overall behavior, how to get a representative sample, that is very important. So for that you have to work out the purpose for what you want to do, what so what kind of techniques or what is your aim, right. So for an example, for XRD, right, a few grams of sample would be required, but for strength determination few grams will not do anything, right. So it depends on the goal, what you want to achieve, right. So also need to have a general idea about the internal structure, right. So sample from interior, for an example, if you are doing a compression test, right, you after compression test you may have induced micro cracking in lot of samples, right. So you have to be aware of that, right. So you want to make sure that the sample you are taking is free of that, right. So if you are looking at microstructure for an example, right. So the internal cracking will affect, right, you will not be able to determine lot of characteristics, right. So these are the things you have to keep in mind, and if you are looking at externally induced deterioration, right, could be any type of attacks like salt attack, sulfate attack, right. Now it is important to get samples at multiple samples across the depth, right, because you are exposing your sample, or maybe in real life your structure is exposed, and characteristics across the section, right, will depend on the extent of diffusion of that aggressive salt or solution, right. So you need to have samples across the depth, right. So these are the few basic things you have to keep in mind, right. What you do after sampling, once you have taken sample, you have to grind it, right. For grinding we use ball mills, disc mills, different types of mills are available. Ball mills are preferable for many applications as they generally provide a narrower particle size distribution than disc mills, that is a comparison, right. And you have to always keep in mind there is a difference in laboratory and industrial grinding, right. Industrial grinding may be harsher than laboratory grinding, right. Here you see plot volume fraction versus particle diameter. What you see here, it is the effect of grinding time. So 30 seconds to 300 seconds. If you are grinding for 300 seconds, what will happen? You are basically shifting curves this way. You are making your powder finer, right. So these are the things you have to always keep in mind. Suppose you adopt different types of grinding times for your samples, so that will affect your properties, right. Also you have to keep in mind the temperature rise, right, which occurs during grinding, right. You are grinding for few minutes, right, that is going to lead to increase in temperature, and that will have effect on your sample, right. Let us see what happens. So in this case you see this is a cement paste sample, right, X-ray diffraction, basically it is X-ray diffraction, you see intensity versus 2 theta, right. So here is the comparison between mechanical grinding and grinding by hand, right. Imagine you have two different processes. In one you are mechanically grounding your sample, in one you are hand grinding. So see the effect, especially if you pay attention to the peak E. E is basically Ettringite. It is one of the phase you have in your cement paste, Ettringite. Okay. So the intensity gets affected, right. So in mechanically ground sample, the intensity is lower. You see it clearly, right. It has to do with the temperature rise. If you grind like in mechanically ground sample, maybe the temperature was higher, it led to the decomposition, part of the Ettringite got decomposed, right. Here also you see that in this case on the right plot, you see in the when you do hand grinding, you have Ettringite, but when you do mechanical grinding, you see a formation of monosulfate. Basically it tells you some of the phases which are present in your sample may get affected by the temperature rise during grinding. Okay. One of the most critical steps is hydration stoppage, right. So why do we have to stop hydration, right. We are talking about the cementitious materials, right. Basically we mix cement and water and let it hydrate, and during the hydration you have formation of calcium silicate hydrate, cement hydrates continuously, right, and gains strength, right. So why it is critical? It is critical for establishing the correct age, right. If you want to understand the effect of degree of hydration, right, if you want to compare different samples, right, you are talking about 1 day old sample, 7 day old sample, 28 day old sample, right. So you have to make sure that you collect the sample, stop the hydration so that no further hydration takes place, right. Also particularly important for techniques that employ vacuum. Suppose other techniques may need vacuum, so you have to make sure that your sample does not have moisture. So in general, better to remove water before long term specimen storage. Like what usually we do, we collect the sample, right, we grind it, we stop the hydration and then store it for some time. Then we can do analysis depending on availability of instrument. That is the usual way, right. Not all the time you can do or you can do a test immediately after, right. Suppose you want to test it after 7 days, you go to the field after 7 days, but you can't carry out all the techniques on the same day, right, ideally. So what we do usually, we collect the sample, then treat it, stop the hydration and store it. Then depending on the availability, and we do the test, right. But there are a lot of other techniques which you will learn, like in this case it is X-ray diffraction, scanning electron microscopy, you have other characterization techniques. For that you have to make sure that you are stopping the hydration, right, because lot of techniques are sensitive to water. First of all, like SEM you can't carry out on the hydrated sample, like without treatment. XRD may not get affected, XRD you can still do, but since we are you are not following different sample preparation processes for different techniques. Usually we want to follow a same sample preparation technique, then get the sample and use techniques, right. So there are different techniques for hydration stoppage, people have used, but there are always some advantages, disadvantages. So you see oven drying, vacuum drying, freeze drying, solvent exchange. What do you mean by oven drying? You are putting your sample at really some high temperature so that remove the water. So idea is to remove the capillary water, right. How do you stop hydration? Your cement, you mix cement and water, you have formation of hydration products like calcium hydroxide, calcium silicate hydrate, Ettringite, right. Also you have some capillary water left. So you have to remove the capillary water. How do you remove? One of the simple thing comes to mind is, why don't you heat it up, right. So oven dry. Vacuum dry is you put it in some vacuum, right. Freeze dry, you freeze the water, then let it sublimate, okay. Solvent exchange is you are using some solvents which are miscible with water and then let it evaporate, okay. We will go over it. So oven drying, it's like complete removal of free water at 105 degrees Celsius. If you treat your samples, cement paste, concrete at 105 degrees Celsius, then you will remove the capillary water. Okay? But the issue is it is very harsh heating. Such heating can alter the microstructure because you are letting your sample undergo 100 plus degrees Celsius temperature, right. So, sometimes it can even destroy phases, like for an example Yttrianite gets affected if you go above 60-70 degrees, right, you will start seeing the effect. Even on CSH you will see some effect, right. So, we are talking about 105 degrees Celsius, although you are removing water, but you are affecting other phases also, right. So, see the issue. Lower temperature heating can be adopted, yeah, you can do that, but you are not sure then whether you will remove the complete free water or not, right, that is the challenge. If you can use 50 degree C, 40 degree C, but then it will take forever and you are not sure when you are going to remove completely, right. Usually it is combined with vacuum drying. Make sure that your sample is in vacuum. Okay. Freeze drying is you first lower the temperature immediately. So, you freeze the water, right. Now, water is frozen and now lower pressures can be used to let direct sublimate to of freeze water to gas phase. So, we allow sublimation. So, it will direct convert to gas phase, right. That is how we are removing the water. So, it is useful for studying early age cementitious system during setting. Suppose you are interested in cement in few hours, like which are 2-3 hours old, or very early age cementitious system or biological and soil system, that is where it is used. Most commonly used technique is solvent exchange, right. So, what we do, idea is we immerse samples in acetone or propanol, isopropanol for a few days. Okay. Idea is, so alcohol it will mix with water, these are miscible liquids, and then we use removal followed by vacuum drying to remove the solvent. Then we want to remove the solvent, right. So, let it evaporate. So, that way we remove the water also, but may tend to alter some phases. There are some challenges. Molecular size of isopropanol may prevent exchange from smaller pores, right. These are the few challenges, although you are using it, but are you sure that you are able to remove the water from the smaller pores. So, here is again advantages, disadvantages, you can go over the list, but let us see solvent exchange, right. It is easy to perform, you have to just submerge your sample to isopropanol, acetone. These days most commonly you use isopropanol, acetone is harsher. Preserved chemically bound water, so it usually preserves your chemically bound water, preserves microstructure, removes soluble ions from pore solution. Direct drying is also easy to perform, right, in terms of disadvantage is it will affect your chemically bound water, like direct drying. Microstructure generally may also get altered because you are using high temperature, right. So, you can go over this list, it will give you some idea about the advantages, disadvantages of these techniques. Okay. But suggested use also you can see what is suggest. So, stop samples for XRD, NMR, MIP, SEM analysis. These are the techniques with isopropanol and dry afterwards of few minutes at 40 degree C to remove the solvent. Alternatively, when using slice, they can be placed on dry lab paper and then compressed air can be used to quickly dry both surfaces. Okay. These are some of the processes you can adopt when you are characterizing your samples, right. But you have to make sure that you are following the same process, because slight difference will cause also difference in your properties, very important. Sample storage, finally comes to sample storage. You want to store your sample so that nothing is altered, right. So, obviously you want to make sure it is free from moisture absorption, if there is a moisture, then we are talking about again cementitious material, right. So, cement will react and hydration will take place, which you do not want. Carbonation is a realistic possibility. You have a calcium hydroxide in the system, calcium hydroxide tend to carbonate, form calcium carbonate. Also you have instances of carbonation of calcium silicate hydrate. In this case you see this is a fresh slice, this is a 2-hour exposed slice. What do you see? See occurrence of this Cc, Cc is carbonate, okay, calcium carbonate. So, when you are exposing it to atmosphere, you are seeing the formation of calcium carbonate. So, you do not want that, right, because that is altering your phase assemblage. So, these are the things you have to keep in mind. So, usually you store your samples. So, after solvent exchange, you dry, you remove the solvent and store it in low vacuum continuously. Okay, now we will come to sample preparation for XRD. So, you got some general idea, right? How do we stop the hydration, and what are other things like grinding which can affect your properties. So, appropriate sample preparation is critical for X-ray powder diffraction analysis. Intensity and peak position should be unbiased by sample preparation. You do not want to adopt a sample preparation which will affect your sample, right. So, it should be unbiased by sample preparation and sample inherent problems. So, basically you have to take care of two things, one is particle statistics and one is preferred orientation, two things. So, particle statistics, you want to make sure you have enough number of crystals, crystallites which diffract at a certain angle, right, and you have enough, basically you lot, infinite or very large number of. So, you will deal with the particle statistics. Also you want to make sure the crystallites are randomly oriented, because you have lot of plate like structures, lot of needle like structures in your cement paste. So, you want to take care of preferred orientation. So, these are the two things you have to take care of. So, ideally this is ideally powder should be ground to particle sizes of less than 5 micrometers, that is the ideally you have to do. As we saw yesterday last lecture, because there are a lot of issues we can resolve when you use the fine powder. So, insufficient fineness is one of the most common sources of error in quantitative phase analysis of Portland cement. If you want to do quantitative phase analysis, if you have insufficient fineness, that will cause a problem. Okay. Microabsorption, extinction effects can be best mitigated by reducing particle size of powder. So, that is the key, you have to make sure you are using fine powder. Okay. So, grinding should occur without sample fractionation, phase transformation, decomposition, amorphization. You have to make sure that. So, you have a sample, you grind, and then if you analyze your sample before and after grinding, you should not see these phase transformation, because otherwise that will affect your, that means you have changed the sample. Decomposition, you should not grinding should not lead to decomposition of a phase. We have saw when you grind too much or you adopt mechanical grinding, right, depending on the temperature rise, you may affect the phases. So, those things you have to keep in mind, because that will change your phase assemblage. Amorphization, So, over grinding issues can be avoided by using liquid medium. Now, how do you resolve it? You can use a liquid medium while grinding, right. So, that will dissipate the heat, but liquid medium we can't use water. Water will then again react with the water. So, we can use the other these are the examples, isopropanol, acetone, ethanol, these are commonly used for Portland, clinkers, cements. Okay. So, that you are making sure that there is no further hydration, at the same time you are making sure that heat is dissipated, so the phases are unaffected. Is okay. So, now you have a sample, now how do you mount for X-ray diffraction? So, sample surface area should be large enough to avoid beam overflow and sample transparency aberrations. Okay. You want to make sure you have enough thickness of the sample, because you it is easy to visualize it. So, you have a sample at lower angles, what you will see, your beam will be like this, lower angles, we are talking about theta, right, you are changing your theta to theta. So, your sample should not be small enough, so that there is a beam overflow. So, you have this beam, right, at lower angles. So, you see it changes like this, right. You see your think of X-ray diffractometer, what you are doing, you are moving along the circle, right, theta from smaller angles to large angles, right. So, these are the issues. So, you have to make sure you have enough surface area, right. So that is why your sample surface area should be large enough to avoid beam overflow, and sample transparency, it should have some thickness, few millimeters of sample thickness is good enough for X-ray diffraction of cements, right. Sample should be flat without roughness, not tilted, in order to avoid peak displacement. You have to make sure your sample is flat, should be without roughness, not tilted, because that will again affect your peak displacement. We talked about it, right. If it is not in focus, then you will see the peak displacement, and also you may have broadening associated with the sample height difference. See, again re-emphasizing, very important, platy-crystallites or Portlandite AFM phases. So, these are the phases commonly present in cement paste, and they have plate-like structures. So, platy and needle-like structures, needle-like eternite crystals may undergo preferred orientation, right. They will tend to orient in a preferred direction just because of the nature of their shape, right. So, backloading of the powder sample is recommended to reduce preferred orientation. Backloading means, so when you do powder diffraction, so you have a sample holder, you put your powder, you press it, right. When you are pressing it, you may lead to preferred orientation, you are pressing your sample, right, from the top, right. So, backloading means now you are flipping your sample and then analyzing that part. So, that can help with the preferred orientation if you see preferred orientation in your sample, okay.